In this video, I'm going to give a brief overview of the content we're going to learn in week 10 of the quarter. It's all going to be about acids and bases. And I'm recording this a little early in case I just got my booster and I'm already starting to feel a little sick. So I wanted to get this out just in case it's helpful as you tackle the material we're going to be learning this week. So the content that we're going to go through has 3 different modules, and it can generally be broken up into identifying acids and bases and thinking about their chemical reactions. We'll also talk through how to characterize an acid or a base and talk about how to characterize its strength. And we're going to focus on acids instead of bases. It's the same principle for bases, but we typically work from the perspective of an acid, especially in like everyday life. And lastly, we're going to talk about buffers. And I would review all of these before coming into lab or tackling the lab, because we're going to look at all of the concepts in these 3 modules when we actually do our lab this week. So let's start with just identifying acids and bases in general. So when we think about an acid and a base, there's several different definitions, and we're going to focus on the Bronsted-Lowry definition, which says an acid is going to donate a hydrogen cation, which is really just a proton. Right, H plus. A hydrogen is an electron and a proton. So if it's got a positive charge, it's really just that proton. And a base in a chemical reaction will accept a hydrogen cation. And so bases typically are going to look like things that have, ooh, that is not useful, lone pairs. Sorry, 1 second. So these are going to have lone pairs. Sometimes they even have negative charges. Some examples, the ones you're going to see the most frequently are going to be OH minus or NH3, which is not negatively charged, but it has a lone pair. An OH minus anion has 3 lone pairs. And an acid is always going to have a hydrogen in it. So an acid has to have a hydrogen. Some common acids are usually a hydrogen paired with a halogen, like HCl, HF, HBr, but it could also be paired with other things, usually an hydrogen bonded to an oxygen atom. So like an example would be a hydrogen bonded to an oxygen atom and then bonded to a carbon with a double bond to an oxygen. Oops, sorry. So this is like an organic acid or a carboxylic acid. So these are just a few examples. There's other ones. There's definitely a lot more acids that you'll be introduced to in this chapter than bases. So by no means do you need to memorize them, but it's kind of helpful to be able to recognize them. And when I'm looking for an acid, it's got to have a hydrogen. And when I'm looking for a base, it has to have lone pairs. And a lot of compounds will have both those things. So it takes a little bit of intuition, which no one expects you to develop in a week. All right, so that's an acid and that's a base, and you'll be expected to start kind of identifying which ones are acids and bases in a chemical reaction. There are 3 types of chemical reactions that we're going to look at. We're going to have neutralization reactions, which we've already seen. These are when we bring together an acid and a base, and it forms a salt and water. We're also going to introduce acid and base dissociation reactions. So in these dissociation reactions, so when you see this, let's get this dissociation word, it means that one of the reactants is water. For an acid dissociation, it's an acid plus water. And it's going to form the conjugate base of the acid plus H3O plus. The base dissociation reactions will be a base plus water. And that base will form its conjugate acid, which is really just the base plus another hydrogen, and OH minus. So what's happening in these is water is acting as either an acid or a base. Which is pretty cool. Like, wait, water's doing both things, which really then introduces this idea of amphoteric compounds, of which water is one, which means just both an acid and a base. In fact, since water can act as both an acid and a base, it could donate a hydrogen and it can accept a hydrogen. We actually get something called the autoionization of water. So we have H2O plus H2O, and one of these is going to act as an acid, and one of these is going to act as a base. And when that acts as an acid and as a base, here, let me get another color. One of the hydrogen of the acid is going to go and be accepted by the base. So it breaks the bond with the acid, it forms the bond with the base. And it's going to form OH minus and H3O plus. And that OH minus, right, is now the conjugate base. And the H3O plus becomes the conjugate acid. And so this we call the autoionization of water. And it allows us to basically convert between concentration of hydroxide and concentration of hydronium ions when we're characterizing the strength of an acid or a base, which is super interesting and extremely handy. Yeah, because at least in solutions where the solvent is water, because if water is around, then this reaction is taking place. All right, so let's talk more about that characterization of an acid's strength. So there are kind of two different types of thinking about how strong an acid is. There is, I like to think of as like something that'll hurt you. So it's like dangerous acid. And then there's also the strength of the acid. And these aren't the same. So a strong acid will dissociate a lot. So that acid dissociation reaction we showed, all of that acid will dissociate into its conjugate base. Or I guess we could say if we're measuring strength, which is a range, we could say it's really the amount of acid that dissociates in water. Whereas the dangerous amount, like what acid is, it's about the concentration of H3O plus in solution. Because the more of that that's around, the more like you would actually damage your skin. And so that's what we usually think of as acidity versus acid strength. And so we're going to characterize these in different ways. Our acidity is going to be characterized by pH, and the strength of an acid is going to be characterized by Ka. That's the equilibrium constant. We have learned about those. So we're just going to apply everything we know about equilibrium constants and use them to understand Kas. And it's the exact same thing. We just put a subscript A so you know we're talking about an acid. Guess what? If there's a subscript B, it's still just the equilibrium constant. It's just the equilibrium constant for a base. So like we learned about equilibrium constants, Ka is always going to be equal to the concentration of the products over the reactants. And our pH, which is going to be a little bit different, this is a measure of the concentration of hydronium ions on a logarithmic scale to make it a rounder number. So that way we don't always have to write times 10 to the -7th or -19 or -3. So pH is going to be equal to the negative log of that H3O plus concentration. And you might see this written as H plus instead. If you have protons floating around in water, they're super, 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 super tiny compared to the water. And so they will form a bond. They'll like bump into a lone pair of a water and just stay there. So if you have H plus ions in water, they'll really be H3O plus ions, and you can use those interchangeably. All right, so we'll measure these, and we can use that acid base and the autoionization of water, because it's amphoteric, to convert between H3O plus and OH minus ions, which allows us to also measure things like POH. So let's take this over here. So I can write the equilibrium constant for the autoionization of water as the concentration of hydroxide versus hydronium ions. And when I do that, I can, this Kw is always going to be equal to 1 times 10 to the negative 14th. So I can convert between OH minus concentration with anything that has water and H3O plus concentration, which means I can also calculate POH, which is the negative log of OH minus concentration, which is cool. And we use both of those scales, pH and POH, but pH is used a lot more. So I care that you know the pH scale better than you know the POH scale. All right, so that's how we're going to characterize acid strength. You can do the same thing with base strength. You can calculate Kb, you can calculate POH. Now let's talk about buffers. So a buffer is going to be a weak acid plus its conjugate base, mixed in about equal amounts, or 1-to-1 ratio. When you have a lot of this solution around, then if you, let's see, if you add an acid, a strong acid, to something that has a buffer system or a buffer solution, then you're going to be able to neutralize that strong acid or weak acid, whatever you've added, because the acid added will react with the conjugate base in the buffer to form the weak acid of the buffer, plus the conjugate base of the acid you added, which won't be acidic, right? So if you instead, so that's kind of one version, you can also do if we add a base, it's going to be the opposite. So we're going to add a base, and it's going to react with the weak acid from our buffer. And it's going to form the conjugate base from our buffer, plus the conjugate acid of that base we added. And so what we're doing in both of these, right, is, in both of these, we are neutralizing an acid or base that's added and making more of something we already have in solution. So let's put this. Now, the cool thing about buffers, right, is that when you have a weak acid and a conjugate base, a weak acid is, this means that it has like a, a Ka less than 1, which means that there's going to be an equilibrium between our weak acid and its conjugate base. So if we increase either one of these by adding an acid and it reacts with one, it forms more of another, then we will disturb equilibrium, and equilibrium will reestablish itself over time. So this is basically Le Chatelier's principle, maintaining a pH if we have about this 1-to-1 ratio, which is kind of key. So that way we can react with either an acid or a base added. And this is super cool because it means that we can have a chemical reaction taking place. And if we generate an acid or a base, we can essentially neutralize it with a buffer solution. And this is important if we're dealing with living organisms that live in a very narrow pH range. Like humans, I think, are between it's like 7.35 and 7.45. Like our blood needs to stay in that range. And so we actually have a buffer system within our blood to help us do that. We have actually several mechanisms to try to maintain the pH of our blood so that way we can survive. And so this is one way that we'll do it. So that's my brief overview of of acids and bases that we'll be learning about this week. Hopefully this overview helps you as you start tackling the lectures. That'll go into a lot more detail on all of this.